So the last homework, usually like I do like 2 homeworks for the last homework, but I don't know. If you guys want to do that, like for the qualifier, that'd be the reason, for you to do like the qualifier. There'll be like 2 questions, yeah. Or I could just do 1, like it doesn't matter. Just 1 on, like I'm gonna do,
When are we turning?
huh?
When are we turning again?
End of the week, I guess, end of next week. This week and then next week would be like the end of next week.
Okay, end of the next week.
Yeah.
Okay.
What do you think?
Okay, give it a shot.
Well, we could make it like if you want to do the 2, you can do the 2. That would be easy. That'll be better, right? And then because some people, like if you're in chemical engineering, there's no reason to do 2. Right? 1 would be good. 1 on machine learning, but it's individual, right? So yeah, it's my group.
Yeah, it's easy, yeah.
So, all right. So what? Yeah, I think that's the best way. Is just I'll give you 2, but you can just do 1. If you want to just do 1, you can just do 1. But if you do 2, I'll give you 2 grades. It'll add it somehow. I'll figure it out. I think everyone's going to get an A anyway. Actually, the grads, there's 2 guys that haven't missed 2 quizzes. So they're like looking at a B. They haven't turned in the things yet. So, but if they turn it in, that'll be okay. But anyway, so all right, so we can do that. That sounds good. All right, so I wanted to do this week like machine learning, artificial intelligence stuff.
Well, we don't with the membrane.
Yeah, the membrane's done. It's well done. It's like 2 weeks kind of full on membrane. It seemed like the way it worked out, that was kind of necessary. Let's see. Where is the slides here? No, when you do the PhD, you have to take an exam.
Okay.
Yeah, so
That's called like qualifying.
yeah, so if you let's see. So we've got my page. Like there's some all the old qualifiers here, like so you take 1 and I think it's like 3 of them you take, right?
Okay. Also, the other past questions that one.
Yeah, these are past questions.
Remember, it's like they take like whatever it is that they want. And then ask questions.
More general. It can be anything.
That can be anything.
Yeah, yeah. But you only have to get a 60 to pass it. Which means 60 total of all the grades.
Okay.
Average of 60. Yeah. So it means you need to know something about what's going on.
Yeah.
You don't need to be perfect. So if you kind of generally indicate something's cooking in your brain, that should be all right. But if you just complete blank, that's not good. So, but if you can kind of piece together some story, it might be the wrong story. That's okay, as long as it's kind of like something's cooking there. If you qualifier, you can take it twice. So you could probably, all right. Also, say you failed it twice in materials, you take it twice in chemical engineering. So it depends how much time you want to spend taking qualifiers. At some point, all right, in some sense, like they talk about the master's, like it's a working degree. In other words, the state pays for people to get masters.
Yeah.
But they pay per head for undergraduates. That's how usually gets money by per head for undergraduate. Then they pay per head for a master's student. But the state doesn't pay anything for PhD students. So they're not supported by the state. No, only for masters and undergrad, because those are called working degrees by the state. That's in the whatever the Constitution. It means like you can still get a job if you have a master's and a PhD. You're gonna go off and do some fluffy thing. It's not contributing to society. I think that's the main idea.
I would like in South Africa, for every PhD that the institution graduate, the state pays the institution money. For every PhD or master student that the institution graduate, the states also pay them.
Uh-huh. Yeah, well, we work that way too, but not with PhD, just with masters. The people, there's kind of a general theme of kind of anti-education going on in the US right now, you know. So I mean, this is part of it, I think. But it really goes back beyond that, because I mean, in other regimes, the same rule. That's why Ohio State has 80,000 students, because they're being paid per head. So there's no reason for them to cut it to like 10. If it wasn't per head, Ohio State would be 10,000 students. Like Case is 10,000. Case Western, they're not being paid per head. Yeah, they're private. And then Notre Dame is 10,000 students, even though they have a good football team. Like their football team's this huge thing. It has to be like Michigan, right? I mean, Michigan's another 80,000 per head student paying place. So it's kind of weird. The Midwest especially is this per head payment thing to these huge universities. Yeah.
Which is like counterintuitive for this practice.
Yeah. Well, no, we got people online, man. Come on. It's half virtual. I mean, it's not supposed to be. I think it's breaking some rule to do that. Anyway, it seems like, you know, it seems like it's okay, I guess. It'd be nice if there was more. Anyway, it doesn't really matter, you know, I guess. Anyway, yeah, so I'll do that. I'll give you two things, and if you want to do one, just do one. Yeah. But probably the one to do would be the one on artificial intelligence thing.
So if you give two, all will be on
No, the second one will be like just a qualifier question.
Okay.
The general question.
Okay.
Yeah, and then the one will be on this stuff.
Okay.
This stuff isn't too bad. So anyway, artificial intelligence, the future of driving, right? This is it. Person in the driver's seat is only there for legal reasons. But look at all the information, so that it's identifying all the things instantaneously, you know. And it's just like over here, look at all the information it's getting. And it's just making decisions based on all that information, right? So you can imagine, like, I mean, this could replace a grad student, pretty much, you know. Give them like,
what is the danger of this?
it's safer. This is safer than.
What's the danger?
There's the danger, there's a lot of danger, but this is safer in general than you driving a car. You know? Let's face it, like, look at all the information it's taking in. You can't possibly see all that information and process it. Like, your brain doesn't work, especially when you get to highway speeds, right?
Yeah.
So, I mean, this is much safer. I mean, it's not comparable, right? This thing is much safer than a person. I mean, it doesn't have an attitude. Like I got a Bolt, you know, it's got auto assisted cruise control. And I noticed, like, all right, I get on the highway and I just want to get up next to the guy in front of me, and as fast as I can go past them, cut in, you know, this thing just like, it's going to keep this space. It's like, it's kind of like having your mother behind the back seat, you know, but basically it's so much safer. And I realized, like, if I just left that space all the time, like, I could probably live longer, you know, and like a lot fewer accidents. And there's none of this business, like, it doesn't have an attitude about, oh, what's that guy thinking in that other car? Or like, you know, for me, I'm always thinking like the other people, like how, and it's a competition type thing. Like that's completely out of it with this. This is just doing the job and getting you there.
You know how they have like the main sensor ones?
Yeah.
Like, not even AI, just like back.
Yeah, I
like
get that too, yeah. Yeah.
I read somewhere that like that is more costly than, and that include like, and the rest of the stuff that they try to include. That is more costly than the AI stuff.
Is that right?
Yeah.
Huh.
And it was like, oh.
Well, Tesla didn't do the, because they couldn't get chips or something for the radar part of this, when they just do it with cameras.
Yeah.
So there was a big argument with them, I guess, about that. Anyway, so the radar, I think, is better, I guess. I don't know. It's hard to tell. Anyway, this looks pretty sweet. Like they have this thing down. So there's that business. And then there's like, I went over to the Rumpke Recycling. I got a couple films there. So AI robot to get high density. They aren't great videos, you know. Hopefully it'll play them. It plays on my computer. It just downloaded it. It finds the milk jugs, and it's been trained by a person to say like that isn't a milk jug. Like here, it'll say like no, and then like it just has some video cameras. It can go much faster than a person, you know. And there's like 3 of these running constantly. This is a combination of machine learning and artificial intelligence. It's just using optical video camera to identify milk jug.
So there's the camera on the top.
It misses. I think it, like you could see, it missed right here. Yes.
So there's the camera on the top.
So it's continuously running 24/7. The garbage, all your recycle you throw in, and then that selects out the high density polyethylene. That's right down the street from here. It's on Vine Street. Yeah. You can walk to this place. Yeah. I'll return that you can walk to it. There's that business there. And then something simpler, like they have, let's see, this is just IR. So they have an IR, a bright IR camera, and PET has a certain band. They've selected one band in the IR absorption for PET, whatever the aromatic ring or something. And then when it sees that, it pops air, it blows air, and then the bottle, then there's this garbage is going down here, and there's a little wall, and then a top kind of, so it pops the air and pushes the PET bottle over the top and into the other thing. This thing's been around for a while, like longer than that artificial robot thing. Also, fewer moving parts. Like the other thing, you can see like if it hits on a brick or something, it's going to just jam up. Right? But, so anyway, this thing's, the conveyor belt just goes through. It's just got IR sensors. It says like that's PET, poof, and then like just right after that poof, and then the bottle goes over the lip. Thing. There's other parts of this place that are like people. I can show you the manual labor part of this thing. Where is this? Yeah, other robots get IR separate. And just the conveyor belts. That's just a picture of like how much this operation does, right? There's a lot of people like kind of picking out the different pieces of this stuff. So there's human input to it. Manual sorting. So this, we were standing there, and so the big problem is the lithium ion batteries. In fact, this place burned to the ground like 5 years ago because a lithium ion battery got in, and one of the machines chopped it, and then it blew up, and the whole place burned. You know? So they're really serious about lithium ion batteries, especially the weed whacker batteries are kind of large, you know, and those can get into the recycle stream. That's a big problem. Anyway, manual sorting, air to separate. So yeah, and then I just show you a couple other things that they, manual. So there's manual. we were standing there and a battery came along, and like the guy who was picking it didn't see the battery, and the guy who was showing us the tour said, "Hey, there's a battery." It was a big lithium ion battery, you know. So anyway, air, and then they use the air to separate the like the boxes, like the airborne. This is like kind of gives you an idea of like, so this is 24/7. There's a crane over here that's just loading the recycle stuff into a conveyor belt. Big time operation. Like this is the all the recycling in Cincinnati goes to this place. So there's a bigger one in Columbus apparently. Like Columbus has the largest, one of the largest in the country. So, and the same company runs it, Rumpke. Anyway, so that's kind of like where this stuff is going, you know, this artificial intelligence, whatever. That's part of it. So so there's a lot of different features to this. You can see how this might so in materials, this thing lists the 5 areas, you know. So you have this is just a prelude to it. They had a whole issue on just artificial intelligence 2019, but so you have so people are getting money to do research in this area, right? And it isn't exactly, all of it isn't really directly leading to any kind of solutions to anything. So it's just to do the research, but so so training models. So you get, I'll show you with dielectrics. It's kind of seem to be quite a few papers on that. So how you do like a nanocomposite dielectric polymer based material, and how do you optimize it? And you have there's a lot of parameters. It'll be like the shape of the nanoparticle, the size of the nanoparticle, the composition of nanoparticles, the type of polymer, the molecular weight of the polymer, fast transition of the polymer. So you get all these parameters. So you need to get a bunch of data. The whole thing relies on feeding in a huge amount of data. And you need kind of models. Not exactly, I mean, it's not really using models, it's just taking all the data of all the things that have been made. And then you can say, like, is there a linear dependence between molecular weight and the dielectric properties or something like that. So and then maybe it's not a linear dependence. Anyway, so this package is already online, like scikit-learn, Keras, PyTorch. These things are where you can just plug and play. Like most of these are designed to look at like micrographs. So you have like a zillion micrographs of something, you want to identify where the smiley face thing is, or the hexagon ring or whatever. And then you can say, like, you can just shove all those pictures into one of these kind of apps that are online. And then when it happens to pick the hexagon ring, you say yes, or you say no, so you teach it. And then eventually it learns itself how to do it, how to pick out the milk jugs. But in this case, it's some kind of scientific thing that you're doing. So that's like this this week the American Chemical Society, they come out with a article. Let's see, CNE feature article. So this is like this week, right? So analyze visual data. So this is like, because the machine learning artificial intelligence started really with like kind of movie sets or video games where you try to make things look real, you know, it's like pictures of people. So you can make an artificial person. I'll show you later. You can make artificial people that look like real people, that are based on feeding them a lot of different people and have the computer kind of assimilate those or something. They tell it, yes, no, that looks like a person, that doesn't look like a person. And then finally it can learn to make people, like pictures of people that don't exist, like non-people people. that you can't distinguish from a real person. So the same with like this is a 2D NMR pattern. Okay, so you have, let's see, I'm gonna blow this up. You have nitrogen NMR and proton NMR, and it's each of the, so if you took one slice through this, it would be like the proton NMR pattern. And then what you have plotted here is a cross correlation between the intensity for the nitrogen absorption and intensity for the proton absorption. And then the bigger this is, the more they're in sync with each other. So it's a correlation function we're plotting. So like this is correlate with that. So where there's peaks, that means that chemical element associated with that nitrogen peak associates with that chemical element associated with that proton peak. If you have a protein, there's a lot of peaks. There's a lot, and then from that cross correlation, you can identify all the groups. You can also identify like helical associations, like when you have the helix is hydrogen bonding, so there's association between the protons that leads to a shift in the NMR pattern. So basically, this ends up being just a fingerprint. It doesn't matter if you understand what's going on in it or not. I know it's to a computer. It doesn't understand what it is, but it can take that kind of photograph and identify it with a chemical structure. And then if you feed in enough of these photographs and enough of these structures, it can just take those 2D NMR patterns and just tell you what it is. Right? So that's like machine learning, because you trained it with the data. And then it's kind of looks like it's artificial intelligence, because it can tell what that pattern is even without knowing anything about it. So it could replace an NMR guy, I guess. But when it's wrong, you don't know, because you don't know, it doesn't have any idea why it gave you the answer it gave to you. So the problem is like someone has to kind of back check the answers, but basically as a tool, as a routine tool, it's going to make your life a lot less tedious to have that identification process going on. And then you can back check it. This is a heptagons and pentagons identification for a micrograph of something. It just says thousands of atoms, mostly hexagons, find the heptagons. So for whatever reason, you know, they want to do this. Anyway, so there's kind of softwares available to do this stuff, you know, to do this kind of identification thing. I don't know. I just thought it was interesting because that was this week this came out. So it's like pretty active area. So anyway, we got this guy. So anyway, so there's a thing called business analytics, which is almost exactly the same thing, but in business. Right. So it's, and UC has one of the best programs in this business analytics thing. He's got a master's in it. And anyway, so it's a big job demand. Like there's a lot of, I had a grad student get a PhD in materials. And then he said, oh, I'm going to go to business analytics. So he went to California. I think he went to Davis or something. They have a business analytics program too. But anyway, so anyway, that's what he's doing now, is doing business analytics. So basically, this is the kind of thing where you do something like you have a gas station. So it's like you can get the data from the pumps about like day, time of week, month, year, whatever, oil prices. You can feed it. That's called the Internet of Things. Like all the information you could get about a gas station, including like what's going on in Saudi Arabia and everything else, you know, Nigeria, you know, oil price and how it's going to fluctuate. And then you can sort through like, how does that really impact like how you're making money at the gas station? In other words, you set the price, people come in and buy the gas. It's like, how is all that information? So what's the important information? Like out of all the information you have, what's the important stuff that has some relevance? And then you have some model or the machine learning can draw some kind of relationships between the data and what you're getting. You can make predictions and optimize it and implement. Right? So that's kind of the sequence. You're doing exactly the same thing in science. I mean, so it's the same tools you use and the same approach, but you can apply it to research too. That's the idea of this. So basically, it can be applied to anything. You know, like at Amazon, Amazon keeps telling me what you should buy. They're using the artificial intelligence, machine learning. They learn from what you train it when you buy the stupid whatever protein powder. And then like it's going to come and find you a cheaper one. And say, this is better, buy this one. Oh, this is one the only thing that's on their money, basically. So and then so it can work, that can be helpful, I mean, it doesn't have to be an evil thing, but and then it can fail like terribly. Like if you're ever frustrated by these automatic answering and it keeps asking you the same question over and over again, and you don't get anywhere, and finally it just spits you out and the thing crashes. So it can fail like disastrously, or it can work pretty well. So it's kind of like a thing where, anyway, the bottom line is that and there's some issues about proprietary, like who owns what. Like you're getting all this data from people, they're giving it to you free, but then you get a value out of it after data mining. So do you really own that? Can you sell that? Or anyway, so what it comes down to is this thing's like in everything now, like from cars to garbage. Right? It's basically this kind of thing's in everything. So they're breaking it down this way, that in terms of business analytics, they have like the measurements, like whatever data you're going to get, so descriptive. And then there's a diagnostic. So finding out what the important parameters are, like did the weather affect your sales, and then predictive. So how are you going to predict the future? And then in the near term, there's this prescriptive. So machine learning is like predictive, like it can pick out the milk jug. Artificial intelligence is when things start to seem like it's predicting things that it couldn't possibly know. Like it can make a human face. So machine learning means it can tell, like it can identify your face with your cell phone. It can tell you when you need to type in the number. Artificial intelligence is it can make a new face. And it can use that face to
machine learning fingerprint.
Yeah, fingerprint's the same thing. Yeah, but now like the iPhone does a face identification. I don't know about the others probably do too, right? So yeah, so it's just like it just looks at your face. You don't need a fingerprint. So basically that's machine learning. Like it learns to, you have to train it. When you go through that, first you do like train it with your face, and then anyway.
Like recognize your face and then
Yeah, it stores it. Like my phone does that. I just look at it and it opens. Like, so I don't know if yours does, but probably will.
But then with this technology that is doing everywhere now, would somebody clone your face?
Yeah.
Doesn't have access to it.
Yeah, they could. Yeah, that's in all the science fiction movies, right? Maybe get the guy's fingerprint and reuse it somehow, or iris scans. I don't know. I've been watching a lot of those lately, but yeah, you can do it. It's true, but generally, no one's going to go to that bother to get into your phone. Is there really anything that valuable in your phone? I mean, it might make $20 or something, but the cost for doing that's going to be pretty high. Yeah. I mean, they can take it, they can just walk up to you and take it. I mean, basically, like, they don't need to go through all this routine, just grab and go. I mean,
yeah, that's true. But if you grab and go, but just imagine now, okay, I'm using my face to get access to my phone. If you grab my phone and then it's useless to you because you can't get access to it.
True.
So you need me.
You need your face. You can cut your head off and carry it around.
Come back and locate me.
Yeah. I don't know. You can track the phone too and stuff, so it isn't, who knows? Anyway, it exists, right? And it basically you're going to be using it one way or another. Good or bad, you're going to be using this thing. And I think generally it's pretty good. Like it's going to make your life easier. But there are like drawbacks to it, and there's also going to be a lot of debate over it, like the auto driving cars. Everyone's like up in the air about it. It's like it's safer,
Yeah, but of course, that quite a lot of advantages. But then it means that we're going to the era that you don't need to learn how to drive.
Right, you don't need to learn how to drive. That's true.
Just get a car and sit on it and then
Yeah,
drive it all.
right. Yeah, so
What
that's
if
good.
something go wrong? And you don't know how to drive.
I mean, I don't think that's rare, right? I think that generally, I compare that to how many times people get in a wreck and die, or get maimed or something, or they hit someone who's walking or jogging or something, or hit a cat or a deer or whatever, right? So basically, if you compare statistically, you're better off, you know. Once in a while, yeah, something's going to happen, but you know, statistically, you're way better off for the system, I think.
It's gonna be a great if you say that moving all these guys, like, traffic quality,
Yeah,
you go quicker and like better ones.
it's going to be a lot more because the cars can talk to each other.
Right, yeah,
Yeah.
like great for everything, like.
Right, so if no one slows down, if no one goes and stares at the accident in the other lane, then the stuff just keeps moving, or a merge, you know? Like the cars are talking to each other on a merge, that's gonna be a lot smoother, you know? So I mean, basically, or if the cars coming in can slow down to keep the cars on the road going or something like that, you know?
That's in the truck.
Traffic will be much more efficient, yeah, you get there faster. Yeah, and it'll be safer. I'm all for it, you know, and I'm 100% behind it, like, because I've seen how I drive, and I know most other people drive in the same way. Some people are good drivers, you know, but I'm not one of them. So I mean, I'm really happy to let some machine take over that task. It just doesn't. The funny thing is, you can walk and be very polite, you know, in a group of people, and no one's cutting anyone off. But you get into a car, and all of a sudden, everyone's like jamming in to get the next thing, and it's like it becomes this competitive thing. I don't really know what the car has to do with it. Somehow,
No, I guess it's not the nature of human, we're always in a hurry.
but you aren't when you're walking, right? You don't like push someone out of the way and like I'm first, you know. I mean, right? I mean, it's better. The machine's better. You can teach it to do a reasonable thing, and then it'll just do it. You don't have to get involved in this thing. But maybe it's especially true in the US because the people are like independent. You know, and they want to be independent and they don't want to have to rely on anybody. So that's why the car is so nice here. Like everyone wants to have a car. They want to live in the suburbs and get away from everyone, build a big yard and put a fence around them and attack talk. The ideal world, you know. So anyway, so it's the same setup. This is from the data analytics, and it's exactly the same thing that we're talking about, you know. So what can you do with it? I mean, if you're going to screen, like when they do superconducting alloys, they screen any possible combination of materials, just measure the conductivity. So yeah, this is like the perfect thing for that. Like you can just feed in every bit of information, ever measure the conductivity of anything. Just feed it into a computer, have it learn what the good ones and the bad ones are, and then predict what the next one is supposed to be. And I think that someone would have done that. Maybe they have. Then what's the best metal to be used for, like you do that powder metallurgy and sinter it into a part? What's the best metal for that? Well, it's a complex situation because there's a lot of kinetics involved. There's thermodynamics and kinetics. But all that information is kind of available, more or less, not in a good form. So anyway, that brings up like why you would want to talk about the form of the data, you know. So you have, that's one of the things on that web page. Let's see. Yeah. So the form of the data. So this is what the research is. The 5 areas for research. Like one of them is just things that you wouldn't think would even be issues, right? Like, so one of them is like solve the problem, but one of them here, it's a validation of experiment, blah, blah, but one of them is just how do you make the data, how do you get the data in a format that the computer can read? Like say you're a chemist making polymers, right? So you have to take all the possible monomers that you could use, all the possible combinations of monomers, copolymers, and then like get the properties of everything that came out in terms of the molecular weight and the chemical composition, whatever property you're targeting, like dielectric or whatever. You have to feed that all in, but the data that you have is like pictures of molecules. It isn't something that it's not ones and zeros. So it's converting like molecules. So there's money in converting molecules into ones and zeros. In a short, yeah, which is basically, it was done in the 1950s called group contribution method, where you take the chemical groups, you say each group has some kind of property, you can add them together and get things like miscibility or whatever. one from it. So there's already been laid down like how to do this in a sense. Like, its group contribution method is similar to that. But basically, in terms of doing it with computers, that's big money. Like people are putting like $1 billion into that. Like figuring out how to. So that's why they mention in this for chemistry materials are saying like the things you can make money off, basically. Like one is like doing the experiments, one is just figuring out how to put things into numbers, right? And then using it as an add-on to help you interpret microscopy. That's kind of obvious, I guess. And then one is like developing experimental methods. I'm not sure if this is what that is, but one of them is just high throughput data acquisition. So basically, because it needs to have all this information, it's going to assimilate it and figure out what's going on more or less. You need to have measurements. We're going to be doing like 1,000 measurements in like 5 minutes, and then it can feed that data into something, and then the machine's hopefully going to come up with an answer, spit out like that's the best one. Right, so there's a lot of people working in high throughput data measurements, which usually involves a synchrotron because you have a really high flex beam. So you can see that there's mutual benefits to this, like people who build synchrotrons, people who build machines, and then this artificial intelligence people, and there isn't really a product coming out. Like there's the groups of people that all have vested interest in this. Then there's the money sources. So they're pumping a lot of money into it, but there isn't exactly a product that's going to come out of this. You know what I mean? So like there's a lot of people interested in building machines and measuring things, but is it actually towards a goal, and is it going to actually reach any goal? Like, are you actually going to make a better superconductor by doing that? Or is it better to just whittle around in the lab, just have a bunch of grad students playing different stuff in and see which one works? Right, so some debate over if it's of any value, like the value added in it hasn't been demonstrated at all. Like there isn't any, there's no transistor that's come out of this, right? Despite that there's been like $2 billion been put into it, right? But there's no, the result isn't exactly there. Let's see, this thing's messed up. Yeah, that's better. All right, so anyway, so let's see why it's messed up. There's some things it can't solve either. Like it's not going to solve problems that aren't defined, right? In other words, you have to, these are all well-defined problems. These are problems that aren't, the solution isn't defined, but you don't know what's going to be the solution to global warming. Right? There's a lot of different routes that could be taken. So like you're not going to invent the internet by using machine learning. So the thing itself that it's breeding on, the Internet of Things that it's using to make this stuff, it couldn't make that. That had to be made kind of by politics, I guess. The internet was basically made by politics and military, combination of military and politics. Anyway, so that's the money from 2022, $1.6 billion in the United States government. And then with the world is probably like, I don't know, between China and Japan and Europe, I'd say at least 5 times that. So $10 billion, I guess, about being put into this field. That's a sizable chunk of the amount of money being put into research. You can see it spread across every agency, from the military to whatever. NIH is here somewhere. Everyone's here. Department of Defense, a lot of military. And you can see like this is going to be just as much value to companies to figure out the gas price that they should charge. I mean, it's going to be really useful to predict like where the next war is going to happen and how you're going to win it. Right? If you can figure out, you can put in every kind of bullet, what's the right bullet to go kill people or whatever, this could be a huge advantage. Transportation, you can see it's like Tesla or whatever. So everyone wants it. That's why there's so much money. Everyone sees this as the answer. So yeah, there's these softwares, right, that they can just use. So these are like some of them that how to get into this is a whole nother story, and I haven't figured that out myself, so basically within like scikit, there's like different types of problems you would use. It's all using Python and script languages, and it looks like it would be kind of easy to get to access it, but say like if you identify a problem that you want to look at, like nanoparticle reinforcement or something, like hierarchical nanoparticle reinforcement. So like, where is your access point in this stuff? I don't exactly see it. There's a lot of image analysis, identification, taking complex data sets and reducing the parameters, but it isn't exactly clear how this is going to actually help you, when you start trying to use it. There's only a few cases where people have successfully done something and gotten a good result out of it from this stuff. But so nonetheless, like, it's going to be around. I mean, it's definitely going to be around. So there's these three are the three that are like prominent, but there's other kind of shareware. These are basically projects of a group of scientists and industrial people and stuff that just want to have this available as a tool for materials research. So those things are there. This high throughput data acquisition, again, is like, that's a pretty big money maker for the Department of Energy because they have synchrotrons. They're even using it on neutron sources. So this is something that's across the board. And also the instrument companies are developing like high throughput data acquisition. So I think any kind of analytic stuff is going to be going towards this. But then it like, usually you just have one sample, so then the question is like, are you really going to design your experiment to be like, so you have one plate that's got every possible combination of chemistry in it, and then it's going to just stick that into an analytic machine. It's going to zip, 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 get the IR patterns for all of them, and assimilate all those IR patterns. Then it'll combine that with X-ray diffraction, maybe Raman and NMR. So you have the same plate, maybe you shovel it into different machines. And then finally you get this huge data set of all the information of all those different conditions. Then you need to assimilate it. Versus what you're doing now is like, you go and you make 5 of them. This is going to be like you make 200 or 300, maybe 1,000 samples. You're going to make, now you make 5, and from those you interpolate between the 5, like what's the best one. So it's a different approach to it. It's going to be a lot of prep time to make that plate. Then it's going to be huge, and then running the stuff is possible. And then getting all that data and then analyzing it is going to be another nightmare. But say you're a business guy running a research branch of a major corporation. Right. So and he has like all these people, and they've been in operation for 50 years, and they've made every kind of rubber. And they have a warehouse full of rubber samples, right? Maybe 10,000 rubber samples, if they're different ones, experimental, commercial. And they want to know, like, some car company, BMW, wants to have a tire, it's going to be the best grip in the world, so the sports car runs forever or something, whatever. So basically, they already have all the data, and they have the internet, which has a ton of other data. And they're looking at it like, well, we can solve that problem just by having this thing. Like, this will solve our problem. From a simplistic view, the people with money see this as the answer to the problems. In fact, they can see it that all that expensive R&D whole group that I have, I can just get rid of that and just have this. Right? Because I already have made every possible rubber that exists, and I already have data on all those. And what isn't there is on the internet. So why do I even need to have this like chunk of business that I could just turn into increasing the stock price? So for that perspective, like, that's where this 1.6 billion whatever comes from. It's like they're saying, like, yeah, we could dump off the research probably and just go to this. That's not going to work. I mean, so you can let them spend the money, try to get some of that money on the road to it. But basically, that's a pipe dream. Like that the automatic driving car will work, but this kind of thing, You're not going to innovate with automatic driving. It's not going to find the shortcut route, something that isn't on the map. It's not going to find it. Like it'll get you there safely, but it's not going to get you there, find the shortcut, and the shortcut's was going to make you your fortune. That's where the money is. It's not in getting there safely. Getting there safely is like Procter and Gamble keep making the soap. Just keep making the soap, And then you corner the market, you get 60% of the market, and no one's going to beat you, So I mean that's a great business model for this stuff, because then you can just keep churning it. If the problem comes up with the plant, this can solve it. It's the same stuff, it's the same soap. So if someone invents a soap, like a solid detergent or something, that's going to displace your entire liquid detergent field because it's smaller and better, then that can't come out of this. So these quantum leap things are not going to come out of this, and those are where the money's made. For this and then, like say you have this and you're making internal combustion cars, like it's going to make the best internal combustion car. You're going to get good fuel efficiency, but basically it's not going to go and make an electric car because that isn't even it isn't in the data set. If no one's even looked at it, so like Elon Musk, he's not going to be using this. It's going to be like, no, we're going to go this way. And then like that turns like, oh, let's invest in commercial rocket launch. Like this program will never tell you to do that because governments do commercial rocket launches, companies don't. That's kind of like the theme before like Musk came around and said like, no, we'll just do that. So anyway, it's not a bold, maybe you could program it to do like crazy things. That would be a little scary, I guess, but I mean, you could program it to cut people off on the highway, I guess. So maybe you could program it to do something new. But when that happens, that's when I'm kind of opposed to it, I think. Anyway, so there's a lot of this density functional theory apparently is a good thing for this. Like there's a lot of papers on density functional theory, looking at electronic states and how can improve like conductivity and things in materials. Because that generates a ton of data. So you can use a computer program to generate a huge amount of data about the electronic states and materials, and that can feed into this. So that seems to be a natural coupling between density functional theory simulations and this technique, this kind of artificial intelligence thing. And then people are coupling different kinds of simulations with experimental data. So you use density functional, use molecular dynamics to look at the polymer end of things, use density functional for the ceramic part, make a composite, then get some experimental data on the actual properties that come out, then feed all of those together into a machine learning routine and predict the next material that's going to be useful for this. Anyway, this is like that idea of like taking a molecule and chopping it into pieces, into numbers. So these are some of the sequence. This big smiles thing is something from MIT. Again, it's like hundreds of millions of dollars invested into like taking polymers, like figuring out how you would write it into a code to say what that structure is, and then being able to use that code in machine learning algorithms, try to figure out what's going on. So that's one. These are web pages, and they're also like grants, basically, to do that kind of thing. Polymer genome. This big smiles is part of the polymer genome, which is basically this idea of like group contribution, I guess is what it comes down to. Like take the chemical groups, like the amines, the carboxyl groups, and then like each of those has a certain kind of polarity and functionality, and you can somehow combine that together to get what you want out of it. Let's see. Anyway, then there's a lot of methods to do this stuff. Right? So it's kind of listed in this paper. It's a polymer-based dielectrics paper, but yeah. So these things are just new algorithms to kind of look at how do you do this deciding what's the important data and how you're going to be predicting from it. So these are things to identify the materials. Then you have like if you come out with an answer that's wrong and then feed it back in. So it's a iterative kind of decision making things. Neural network is kind of, I'm not sure exactly what these things are really. I haven't used these things, but so basically these are the things that are being used to make decisions. Like this is an example. It's not from this paper. I'm not sure what this came from, but basically you have a test function, so some random function the machine can, like it could be polynomial, just like some number plus some number times x plus some number x squared up to however many you want. And then it's going to have any arbitrary shape because it isn't the right function. So it's got some weird features to it that show up. In other words, if you're looking for the minimum value of this function of x, it's giving you this value, which has nothing to do with the data. The training data is the circles. So you say, so you're going to have an iterative loop where you make your prediction from the model that came out of machine learning, and it's going to try to correct it, and it's going to tell you, I need more data. Like I need more data at that point. So if you get that data, then you can improve your model. And then we'll say, I need more data at some other point, and then basically you can optimize it until you get a perfect fit to predict what the data is going to be. That's kind of, so this is called this Gaussian. What's it called? Gaussian something. Hold on. It's called a Gaussian. Oh, this is pretty far down the road here. Let's see. There's a here Gaussian process regression. That's what it is. Sorry. So the Gaussian process regression is that you take, like he's showing here what the Gaussian, so it's a Gaussian bell-shaped curve. There's this actual value in your model value. And then within that, so how far are you from the standard deviation of what you think is the error involved in the measurement? So you want to be within a standard deviation. Your thing's going outside of it. And so you have a Gaussian function you're using to weight how good your fit is, basically. So anyway, so that's one method to do this, is this Gaussian function to predict like how good your answer is, how bad it is. And then from that function, you can decide like where you need to find more data, like improve your function. Then do that iteratively until you can find the solution to the problem. So anyway, this isn't very helpful because it isn't really of any real data, right? So this is called the Pearson correlation. So you have both your X and Y data have some error involved in them. So you have these correlation functions and these sum of the differences. And then the sum of the squares of the differences give you this regression number. It's going to give you square root of the sum of the squares, gives you like how good your match is between the data. That's called the Pearson correlation coefficient. That's something that's used in the artificial intelligence, like routinely kind of test for if the model's working or not. Anyway, so that's kind of a picture of how this schematic, how this thing works. Let's see. I guess the best thing is to go to one of these papers, We have let's see. So we got it's supposed to be I guess this is a paper in the slides. yeah, so. Let's see. This is just showing this, this is part of this paper, but it's in a separate thing. But basically, they say you're doing dielectric properties. So, and you want to have, there's going to be the polarizer, the field, the energy that you store in it is in parameter you want. So you have a capacitor. Dielectric's a capacitor. You want to store energy in it like a battery. So you put a field on it, and how long it can hold that field. Because when you put the field on it, it polarizes the molecule. So the polarizability is going to be important. And then the kind of the decay time of that capacitance is going to be important. So there's a couple of parameters that give to the final result, which is the energy that thing can store, like the electric energy can store it for a certain short length of time. Right. So anyway, so the permittivity, electrical conductivity, so you want this to be low, you want that to be high. The band gap is going to decide the frequency response of it, right? So you're going to, it also has like the dielectric constant is going to have a frequency dependence to it. So it's more than just at one frequency. It's basically, these are time dependent materials, right? Like kind of like a polymer, like a relaxation, right? If you're making a composite, so the polymer itself is useless, but you can put in like barium titanate or something that's good, has good dielectric constant properties. Then those particles, if they're nanoparticles, can have different shapes. Generally, spheres, rods, or sheets, right? And then the rods and sheets can have different orientations. So you can talk about the XYZ orientation of the rods and sheets. The particles don't have orientation. So you get a lot of parameters for this. So basically, to get that, you can make some samples, but you can't make perfect samples, right? So to get that, you kind of do computer simulations to get the data. So you have data on how the dielectric of the pure materials are, the polymer and the ceramic. This orientation stuff you can get from the computer simulation. So there's a paper I'll show you next time. They go through like taking all this information from experiment and computer simulation, and they finally actually predict that certain kind of material of a certain size and shape, particles, is going to be the best dielectric material. And then they find out that it's true. They do get a better material from it. So they're using all this machine learning and artificial intelligence coupled with experimental measurements and computer simulations to get an actual result. So anyway, so yeah, why don't we quit there? Yeah, a little bit, but anyway, so we have like 2 more days, I guess. Yeah, I can probably, so I'll just go through the paper on Friday, I guess. We don't really need to do overview of the class or anything like that. You know, I think that's it, unless you want to, but I mean, I think I can just go through the paper on this stuff. Yeah, on Friday.
And the last one, you wrote it on Friday, right?
The last homework thing?
Yeah.
No, I'll do it like tomorrow.
Oh.
Yeah, I'll post it up tomorrow.
Oh. I'm gonna actually put it on that,
Oh, okay. All right, that's pretty good.
It'd be great.
Yeah, you can ask it anything. Yeah, you can ask it anything. It's almost addictive, you know.
That's what about the pop. They give like a full history of like, oh yeah, here's where it's gonna go in the future. Like, oh my God.
Yeah, it's pretty good. It gives short answers. That's the only thing. Like it's not gonna write a book on it.
Yeah.
It'd be nice, I guess, if we gave a little bit more sometimes, you know, but
Yeah, I think that's where you got the like.